Good evening. My name is Oyindamola Abiola. So I'll be talking about smart contract security. The list of things I'll be discussing are smart contract security and blockchain security, smart contract security vulnerabilities, and examples of smart contract vulnerabilities, security measures, and also the conclusion. So smart contracts defining. Let's talk about what smart contract is. So, smart contract is a piece of executable code that it automatically runs on the blockchain to enforce an agreement preset between parties involved in the transaction. So, security in smart contract has been a great deal in the security issues arising from the execution of smart contracts in the blockchain system. Many security issues in smart contract have been reported, leading to substantial financial losses. And also, we need to know that smart contract security should cut across different blockchain platforms, such as Ethereum, Tezos, and EOS. So, for the sake of misconception, to clear misconception, sorry. So we have blockchain security and smart contract security. Blockchain security, blockchain security Okay, blockchain technology basically uses principles of cryptography, decentralization and consensus to ensure trust in transactions for security reasons, and also there are management risk management system and best practice to mitigate the risk of fraud and cyber attacks. So basically smart contract security has to do with the smart contract, not the blockchain. And smart contract, we can say that smart contract security issue, we can call it human error. Yes, we can call it human error. And that is why the smart contract can only be as smart as the person who wrote it. And this, arises from the executions of smart contract functions in the blockchain system. So now we'll talk about smart contract vulnerabilities. So smart contract security has been a great issue, and there are a number of hard lessons learned by developers and users in discovering the vulnerabilities of the programming language, the smart contract logic, and the EVM. As said earlier, smart contract issues in the smart contract are very serious enough for the following. Most of smart contract deals with finances. So, as we all know, most of, I mean, most of the smart contracts that we have out there are handling finances directly or indirectly. Most are actually handling her money directly. And also, so which makes it a very huge deal, makes a very great deal to the blockchain system. So errors in smart contracts once published cannot be corrected due to the immutable nature of the blockchain. So this is explaining that the immutability of the blockchain does not allow us to alter transactions that have been done either by mistake or by error or um, through any means. Once it's done, it's done. You cannot go back to change those transactions. And also, changes in blockchain state generated by transaction of faulty contracts cannot be rolled back. So next, I'll be talking about reentrancy as a type of smart contract vulnerability. So a reentrancy attack occurs when a function makes an external call to another untrusted contract. When the untrusted contract makes a recursive callback to the original function in an attempt to drain fund. When the contract fails to update its state before sending funds, the attacker can continuously call the withdraw function to drain the contract fund. So basically, let's say for example, we have like a withdraw function in a contract, and a user calls the withdraw function. After withdrawing function, the smart contract does not, will not be able to, if the smart contract does not, update the state of the smart contract of the addresses before sending the funds, the caller, which is the attacker, has, I mean, a window to keep calling that function. So that means it is always advisable to make sure to update the state of functions like withdraw function before sending the funds, because an untrusted contract can make a recursive callback to call the function if the smart contract does not update its state before sending it. So that means the normal way that we think is, when they call the function, you send the money, then you update the state. No, you have to call the function, update the state already before you send the funds. So that way, the untrusted or trusted contract or external contract, as the case may be, will not be able to call the withdraw function again because the state would have been updated. So, and we've had several attacks with the reentrancy, and these are the list of attacks we've had so far. We have the DAO hack, which lost which lost about 60 million USD and lent me 25 million. We have Siren Protocol, $3.5 million. Burger Swap hack, which is about 7.2, and also BNB ARC 4 million, and Cream Finance, which is about 18.8, like almost $19 million. So now the next on the list is the unprotected self-destruct. So this vulnerability involve access control in the contract that have a self-destruct method. If the access control is inadequate, user can self-destruct the contract. So what this is saying is that we need to make the access control in our contract very, very adequate, so that we don't give access to users or people that are not authorized to to use a particular function, right? Because if an external person that does not have the right to do some things get access to our contract, they can do anything with it. So for example, we there was this priority wallet hack, which lost almost 30 million dollars. And also, yeah, this is wallet hack. So what the attacker did was, there was a loophole in a library that the contract was using, and it's multi-signature authorizing library. So the attacker used the loophole to withdraw to access the other users wallets, and then self-destruct the contract, and set a self-destruct to the contract. So few ways to avoid this would be to first of all consider the use of self-destruct functionality. That is, if it's necessary, if you really need it, and if it is, consider using a multi-sig authorization to prevent an attack. So next, I'll be talking about unprotected ether withdrawal. This involves access control also. User may get access to withdraw some or all ITA from a contract usually happen by misnaming a function intended to be a constructor or giving anyone access to reinitialize the contract. To avoid this vulnerability, only allow withdrawal function to be called by those authorized or name your constructor appropriately. So this vulnerability also has to do with access control, so that you are not supposed to give access to, you're not supposed to make some access public, right? So, and it happens by misnaming a function, a particular function, or giving access to an external contract, So, and to avoid this, you need to be careful who you authorize the withdrawal function to, and also try as much as possible to name your constructor appropriately, so that the users will not have access to reinitializing the constructor, or doing anything at all to your contract. So the next we have the underflow and overflow. So this vulnerability are created by misuse of variable types and can be exploited by to bypass protection against other type of vulnerability. So overflow of integer occurs when a value exceeds the maximum value that a variable can contain. So this occurs when you have a particular value. Okay, let's say for example you have like a box, and the box has let's say you have like a drawer, and the drawer has four slots, and you are trying to arrange stuff that has you're trying to fix another box that has like six slots inside the four slot drawer, for example. So once you try to force it in, it's not going to get in. You can only allot four slots of the initial drawer or box, whatever it is, to the incoming um box, which has six slots, right? So what happens to the remaining two? It doesn't fit in, then it gets cut off. So that is just like a basic illustration for underflow. So for overflow rather. So for the underflow of integer happens when a value become too small to fit. When this occurs, the value wraps around from the minimum value that can be stored to the maximum. So basically, what this is trying to say is that what this is trying to say is that when you have a value that is too small for a value that is too small to fit into another variable type, right? So what happens is it's kind of automatically generates excess number to wrap around it, to be able to fit in. So which can be stored to the maximum. So now let me take this explanation again. So overflow happens when a value is moved, or let's say it is reassigned to a variable type that is too small to hold it. So an example of this is downcasting. Like example, you want to downcast like 8 bytes to 4 bytes. There is no way this will fit in. So it causes overflow, which is going to cause a big issue in when you have like a kind of calculation in your contract. And this usually happens when typecasting from an unsigned integer to a signed integer variable type. When you are trying to typecast it from unsigned to like a unsigned to a signed variable type, right? So for the underflow again, it occurs when a value is too small to fit. So the value that tries to wrap around it to make it fit can be stored to the maximum. So, for example, let's say you have an unsigned variable of zero value, and then you want to subtract one from it. You have a variable unsigned variable that is one, has zero rather, that has zero value, and then you want to minus one from the zero. Normally it should give you like a negative value, right? But unsigned variable cannot store negative number, so it kind of add values to be able to fit in and then cause the underflow. So um so that is for underflow and overflow. So basically, underflow happens when a value is too small to fit in, while overflow occurs when a value exceeds the maximum value that a variable type can take. So we also have other vulnerabilities. We have the use of tx.origin. We have jump it to an arbitrary instruction. The state change after external call. An example of this is the reentrancy. An example of state change after the external call is a reentrancy, and we have multi calls in a single transaction, multiple calls in a single transaction, and we also have unchecked call returns. There are also other vulnerabilities that I've not been able to mention in this presentation. So now let's talk about some security, general security measures to take note of when you are creating your smart contract. So make sure you mark untrusted contract and also prevent state changes after external calls. Yes, so that means you make your state changes make sure you make your state changes before finally executing the last layer of a particular function, like I explained in the reentrancy. So error handling in external calls, and also make sure you you prefer prefer pull over push for external calls. Also avoid using delegate functions to entrust code. Then manage the function code condition and actions and interaction. And also try as much as possible to keep things simple. Try as much as possible to keep things simple and clear, instead of trying to make things complicated in any way possible. So in conclusion, like I said earlier, right, there are still other vulnerabilities of smart contracts, and the honest truth is writing a completely secure smart contract is a complex task. They are generally prone to various hidden vulnerabilities and code errors that ultimately hamper the security, right? And it is highly advisable to adopt and implement the best possible practices and tools for ensuring smart contract security to a greater extent, and also go through audit before being published. So it is it cannot be overemphasized concerning the security issue that arises with in smart contracts. Make sure you take the possible best practices research on tools that ensure the security of your smart contracts, and also audit before you actually take your smart contract to the public. So I think this is the end of my presentation. I hope you all learned something from it. So thank you very much.